Now that we've seen the surface level performance results of these different matrix multiplication routines, we can look at how to use Nsight compute to understand why the kernels perform the way they do, and maybe get some hints as to how to improve them. So, like I mentioned before, Nsight compute is a tool to record and analyze some detailed information about how a kernel performs. Nvidia calls these metrics. There's two different interfaces that are sort of the same tool. One is the GUI interface, that's the NV Nsight CU binary, and one's the command line interface, which is NV Nsight CU CLI. Basically, there's sorts of thousands of different metrics that the GPU can report to you about what the performance is. These are very difficult to sort of interpret without some assistance. It may be even difficult to figure out what the metric even means, and so the GUI can help us understand the metrics that the command line interface can record. And so what we're going to do with Rye is we're going to use the command line interface in Rye to record the data about the execution, and then you're going to download that and use the GUI on your laptop to analyze that data. So, like I said, there's many different performance counters, and on the bottom of this slide I just have a few of them. You can ask Nsight compute what metrics it supports, and it will give you a very, very long list similar to what I've shown below. But I mean, you can see just from looking at that, unless you're a GPU architect, this doesn't make a whole lot of sense. And this is sort of going to be a theme as we go through this profiling, in that there's a lot of information this tool can provide you, and the trick is really to figure out what you care about and what you don't care about. And of course, the answer to that question will depend on what it is exactly that you're doing. So I'll try to bring some clarity. At the end of this lecture, there's going to be some places where you can read a little bit more about these, but unfortunately, in all the time I've spent working on GPU performance, I haven't found sort of one documentation source that tells you what all of the metrics mean in sort of an understandable way. And to make it worse, the metrics change across GPU generations. So just so we're sort of mentally prepared for this going in, if particular meanings of detailed metrics don't make sense to you, A, you're probably not alone. B, there may be very few people to who it does make sense, and you're not necessarily missing anything. So in Rye, we will record all of this for you. If you'd like to record it on a different system, you can look at the command in the Rye build file, but basically we're going to tell Nsight which kernel we want to profile. And so in this case, we're profiling this MyGem kernel, but we're only going to profile the 6th time the kernel executes. And if you recall back to our process for figuring out the speed of the kernels, right, we had 5 warm-up runs and 5 sort of measured runs. And so this will be the first non-warm-up run that we're profiling. So every time you profile a kernel, it really slows down the execution, so we sort of want to profile as little as possible. So here we're just picking out one of the 10 kernels to profile, since presumably they're all the same. The next part says which section we want to profile. Nvidia groups the different metrics into sections. So basically we're providing a regular expression here that says we want the metrics associated with every section, because we don't want to miss anything because we don't really know what we're doing. Then we tell this thing what the output file will be. So we want to create an output file that's named the same, with the same prefix as our executable, so that we know which relates to which. And Nsight will helpfully stick this suffix here, this Nsight CU prof report on the end for us. And then we just tell it the name of our binary, and it will run our binary for us and only profile the things that we request. And like I said, this is done for you automatically in Rye if you submitted the project, so you already have this. You can also ask the Nsight compute system what sections it is going to profile for a particular run. So by default, it doesn't record everything. That's why we had to provide it with that sections flag. And so if you're curious, we actually do this in the Rye build file as well. You can open the sections text file, and it will show a table that looks something like this to show what it's going to record. So what you're going to want to do is you're going to want to fire up Nsight Compute and go File, and open up all of the first three Nsight CU Prof report files. So those report files for 1-1, 1-2, and 1-3. You'll find that you can open multiple of them at once. They'll be in multiple tabs. We have this cool ability where you can compare things against a baseline. So what you're going to want to do if you want to do that is you'll see this baseline button, which I've kind of highlighted on the slide, and so it will add whatever tab you're in as a baseline, and then when you go to other tabs you will see that at every point along the way it has a comparison against your baseline. So if you want to compare two different implementations or two different modifications of the code, you can use this baseline tool, so you don't have to keep as much in your head. I often find that there's so much information presented that sometimes it's easier to create your own tables and extract out some of the information. And so I'm going to show some screenshots in this lecture of the tools, but I'm going to sort of extract the relevant information out into tables that are a little easier to see. But you can kind of refer to the screenshots so you can see what section I'm talking about, where some of the information is. So the first section that we'll see in compute is something called the speed of light. And so this is basically trying to give you an overview of, compared to the theoretical capabilities of the device, how much of the compute and how much of the memory capacity are you using. These are actually associated with specific metrics, and if you mouse over any of them, you'll see that it will tell you what specific metric it is. So you can see that this basically is just presenting all of those thousands of metrics to us in a more organized way. I think this example was the basic one, but in any case, I've extracted out some of the relevant numbers. So this is quote-unquote achieved percentage of utilization with respect to the theoretical maximum for the basic tiled and joint matrix multiplications, and I've just put the gigaflops on there so you can remember. And so we can see that the sort of use of the SM capability is roughly the same for all three of these. And between the basic and tiled matrix multiplication, the memory subsystem is used sort of to much greater effect in the tiled matrix multiplication. And that sort of is consistent with what we've been taught, right? We switch from the global memory to the shared memory so that we can get some better bandwidth. And so maybe there's a corresponding uplift in the number of gigaflops there, but kind of surprisingly, the joint matrix multiplication, which is even faster, has less of this memory use. And if you were listening before, you might think to yourself, well, maybe that's because we reuse things from registers instead of memory, so we don't have as many demands on the memory subsystem. And you'd be right, but I just want to show you that increasing these things higher and higher does not necessarily mean that performance gets better. In fact, it in some sense is not correlated with that at all. So this is kind of a high-level way to see how the device is being used, but it doesn't tell you whether you're using the device well. So we might want to ask ourselves, well, I was told that tiled matrix multiplication would be much faster than the basic matrix multiplication, and it seems like it's only 1.5 times faster. So why is that true? And why is this joint matrix multiplication so much better? So we can try to understand why that is as we move on through the compute different profile sections. So the first one I want to draw your attention to is the workload memory analysis, and the first thing that's on there is this memory chart. So this is basically a graphic representation of how the kernel accesses different parts of the CUDA memory model, right? And so CUDA has global memory, which you're probably familiar with, right? This is if you load and it comes from the device's memory. There's also something called local memory. You can't explicitly put something in local memory, but this is what happens if you create a fixed size array, but the CUDA compiler can't statically tell what indices you're putting in the array. This will also happen for register spills, so if you try to use too many registers, it will spill some of the values out to this local memory. So basically this also gets stored in the device memory. Then there's shared memory, which you're familiar with, of course. And then there's some things called texture and surface memory, which are basically global memory but cached in a different way. And then you may also remember constant memory. That doesn't show up on this list, but it's also similar to texture and surface memory in that it's global memory, but cached in a different way. So there's a few different parts of this diagram. It might be a little small on your screen, but you can look at it in real life. But basically, it'll tell you how many instructions from the kernel referenced a particular memory space. It will tell you how many requests from memory that generated. And then it will also tell you on the right-hand side how much data is moving between the system memory, the L2 caches, and the L1 cache. And also what's annotated on here is the cache miss rate in those cache boxes. So in this example, the L1 cache, I think it's a hit rate, is 25%, and the L2 cache is 95%. So this can give us a sense of how data is moving and what kinds of ways that data is generated. And so below that, you'll see a huge chart. This is probably too small for you to see on the slide, but it's fine because it has much more information than we need anyway. On the next slide, I think I'll show the particular entries we care about. But this basically shows all the different kinds of memory operations, how many there were, whether they hit in the caches, what percentage of the peak performance they used, and so on. One little caveat here is that it seems to refer to the first level cache as TEX. That might be sort of leftover from older hardware. But as long as if we're willing to accept that and move on, then we can interpret this. So I've extracted some of the numbers here again for the basic tiled and joint. I left the speed of light memory on there as well, just as a reminder. So the third row is what percentage of peak performance we were using for global memory loads that are cacheable. So these are your standard, load something from global memory. And in the basic matrix multiplication, we're at 60% of peak. But you can see in the tiled and joint matrix multiplications, we're at a much smaller percentage of peak. And intuitively, that makes sense, right? Because the whole point of using shared memory or using this reuse is that we don't have as many demands on the global memory system. And actually, in the next two rows, 4 and 5, you can see that. So the number of requests from basic to the tiled multiplication drops from 200 million to 6 million. And the joint matrix multiplication is only a little higher at 8 million. And similarly, you can see that the bulk of that difference comes from shared memory requests. So we've basically turned global memory requests into shared memory requests. We go from 0 shared memory, of course, in the basic matrix multiplication to 160 million in the tiled and 54 million in the joint. Now, the one thing I want to point out here is that because of the way the joint matrix multiplication is implemented, we capture some reuse out of the registers instead of out of the shared memory. The total number of memory requests in the joint matrix multiplication is much lower. But as to answering the question why the tiled matrix multiplication isn't faster, the answer is probably in the next line, which is the L1 hit rate. And so in the basic matrix multiplication, we have a 95% hit rate in the L1. On this GPU, the shared memory is actually the exact same hardware structure as the L1. So basically what's happening in the basic matrix multiplication is we're doing a bunch of accesses to global memory, but almost all of them are being returned by the same hardware structure as in the tiled matrix multiplication. So essentially, most of our global memory accesses are already happening at the same speed as shared memory before we even use shared memory. This is especially true in Volta and up. The memory controllers and caches have gotten a lot more sophisticated, and so you'll tend to see less benefit of using shared memory in these architectures than you would have in some of the older architectures when this course was designed. And so the final thing that I want to say is you can also see the reduced memory traffic in the joint. So this is the final two rows in the joint matrix multiplication. Both the basic and tiled matrix multiplications have about the same number of bytes coming from the device memory. coming from the global memory, because in the tiled matrix multiplication they tend to come from the shared memory, and in the basic matrix multiplication they tend to come from the cache. So it's only the joint matrix multiplication where we're actually sort of reducing the demands on the memory system, which is where most of the performance comes from. So the next section is something called scheduler statistics. So this is where we're trying to understand what instructions the GPU is executing at a given time. And it's broken down into 4 big categories. There's this theoretical, which is basically the size of the pool of warps that a scheduler can pick from, right? So when we're executing things in a GPU, we provide the GPU with a bunch of work to do, and the GPU somehow decides what order to do it all in. And so basically the hardware has a particular amount of space in which it can manage these different warps. And so on this GPU, there can never be more than 16 warps sitting in a scheduler waiting to be executed at a time. And so the number of active warps per scheduler is the number of warps that the SM is actually given on average. So just because the SM can do 16 warps, if we, for example, launched a grid that only had 15 warps in it, then the number of active warps would only be 15 and not 16. So typically we want to see this number of active warps being close to the theoretical maximum. If it's not, that really only comes up through 2 cases. One of which there's not enough work to fill the entire GPU, so that's sort of the first case I mentioned. The other case is if there's a great amount of imbalance in the amount of work given to the thread, or a great imbalance in the amount of work between warps. So right, if some warps are really long, then maybe all of the other warps will finish, leaving just a few warps left in a few schedulers across the GPU. So once we have this pool of active warps, only some of the warps are actually ready to execute, right? They may be waiting on data from memory, waiting on data from other instructions. And so any warp that's ready to go is called eligible. So the number of eligible warps will always be less than the number of active warps. And then the number of issued warps is out of all of the eligible warps, the scheduler can only issue 1 or 2 of them per cycle. So in this hardware, it's 1 warp per cycle per scheduler. So this issued warp per scheduler looks pretty low, but actually the maximum that it can be is 1, not 16. So it's kind of poorly shown in this chart. But one thing I want to say is that you might ask, well, why is it that if I have 4 warps eligible per cycle per scheduler on average, why is my issued warp so low? And that's because just because the average value is good doesn't mean that you don't miss some chances to schedule warps. So if the average is 4 because sometimes it's 8 and sometimes it's 0, then sometimes we'll issue 0 and sometimes we'll issue 1, which gives us an average issued warp of a half, right? So that's kind of what's going on there, potentially. So this is sort of a graph that gives you the same summary of what I just said. So we have some maximum theoretical occupancy, and then the active warps are something less than that depending on how the warps are balanced across the schedulers. The active warps are either stalled or eligible. The stalled ones are the ones that are waiting for data, and then out of the eligible ones, only some number of those are actually executed because the scheduler can only issue so many warps per cycle. And in our hardware, in this hardware, I think it's 2, Fermi and Kepler, 2 or 4. On our hardware, it's 1. So I grabbed a few of those numbers out, and you can see that the issued warps per scheduler are generally pretty low. And also the joint matrix multiplication stands out on the active warps per scheduler. Instead of being close to 16, it's only 8. And we can see why this is later when we look at the launch statistics. But basically, there's a lot of time in this this code where the GPU can't schedule an instruction. So that might be a place to look at if you're thinking about how we could optimize some of these further. And if you're wanting to know why we can't issue an instruction, the profiler can help us with that too. So the next section is the warp state statistics, and this is the section that helps us understand why instructions haven't been issued. This thing on the right is probably too small for you to see, but don't worry, I've extracted some of the numbers out in a table. But basically what we're looking at is on the top there, it will summarize the latency between two consecutive instructions for a particular warp, the average latency. We know that the GPUs are throughput-oriented devices, and the way we handle latency is by having more warp parallelism. So basically, the more cycles you have between two consecutive instructions, the more warps you need in order to hide that latency. And so if you're not issuing warps every cycle, then you can't hide that latency effectively, and it's time to maybe think about why some of these instructions are not able to issue so that you can better hide the latency. And so that's what this section is for. And so basically that is 15 in this small example, which you can't see very well. It's 15.3. And so basically the rest of this chart, the warp state, basically says what portion of that 15.3 cycle average is caused by each of these stalls. So basically the bigger this bar, the more of the time a warp is stalled for that particular reason. They can't always be avoided. Stalls can't always be avoided, and again, they only really matter if instructions aren't issued every cycle. So I'm including it here so we can try to see the differences between some of these codes. So here's our three matrix multiplications again. And so I included the gigaflops in there again. And you can see that they all have wildly different latencies between cycles. So in the basic matrix multiplication, we're at about 30. The tiled matrix multiplication has a much longer latency between issued instructions, and the joint one is lower. So on its own, this doesn't really mean much. But what we can see is that if we look at the stall reasons, this is kind of consistent with what we're expecting. So these stall reasons are kind of difficult to understand. I've included links at the end so you can interpret what these stall reasons mean if you see them in your own profiler. But basically in the basic matrix multiplication, most of the stalling is that the warp wants to issue a load store unit, wants to issue a load or store instruction, right, from that global memory, probably wants to issue a load instruction to get the row or column entry. But there's only so many load or store instructions that the GPU has space to store at a time. And since all of these threads are trying to issue so many loads and stores, that queue of instructions is full in the basic matrix multiplication. In the tiled matrix multiplication, it's the same situation, but we're stalled for shared memory loads instead of global memory loads. And then the thing I wanted to point out is that in the joint matrix multiplication, we have a pretty even distribution of different stall reasons. So sometimes we're stalled because we're actually waiting for data from memory. Sometimes we're stalled because we're at a barrier. Sometimes we're stalled because we're waiting for shared memory. We're never stalled because there's too many device memory loads, so that's a good sign. And occasionally we're stalled because there are other warps that were ready to go, and so we just didn't happen to get picked. And so I would tend to say we have a lower number of stalls across the board, but remember that we also have fewer warps with which to hide those stalls. So this can tell you some things about what is limiting the performance of your code, but just bringing down the stalls won't necessarily improve your performance. So the next section is occupancy. So this basically tells you what amount of the GPU is active at any given time. And so again, this diagram on the left is probably too small for you to see, but if you open up compute, you'll see something similar. So basically the theoretical occupancy limits is limited by the device hardware and launch configuration. So this basically says, if I have there's only so much shared memory in each SM. So if I have one thread, if I have one block that wants to use all of that shared memory, then I can only have one block per SM, and I won't be able to make good use of the device. So this theoretical occupancy is determined by how much shared memory, how many registers, and how many threads you use in your kernel. The achieved occupancy is actually the achieved number of active warps. And so this is kind of similar to the warp scheduler section, except at a block level. So if there's not enough blocks, or if the blocks take varying amounts of time to run, or if the last wave, which I'll talk about on the next slide, is not large enough to fill the GPU, you'll see a lower occupancy. High occupancy doesn't necessarily improve the performance of your code, but if your occupancy is too low, you're not able to effectively hide the latency of all the instructions. So I would say generally you want the occupancy to be high and as a first pass, and you may be able to make further optimizations from there. So when I talk about waves, typically we launch grids that have more thread blocks than the GPU has hardware to actually execute those. And so those thread blocks will be assigned to SMs as those SMs finish them up. So for example, if we have some GPU with 4 SMs and each SM can execute one thread block at a time, this is a little bit simplistic. But if we have 8 blocks, then we might have one wave of 4 blocks and a next wave that's also 4 blocks. And so our achieved occupancy will look like 100%. In this other case where we only have 5 blocks, we have one full wave of 4 blocks, but then one wave where only one of the SMs is busy. And so we'll see much relatively lower achieved occupancy. This would be something like 5/8 achieved occupancy. So if you don't have that much work to do, this can be one reason that the achieved occupancy looks low. It could have nothing to do with the amount of resources you have in a block. It could be the number of blocks that you have. And this is actually the case that we have in the joint matrix multiplication, because we have fewer blocks in this code, and so there's fewer waves to do the entire multiplication. And so basically we have one full wave plus a fifth of a wave. It's very similar to the example I just showed. And so even if the thread blocks are good, they have pretty high theoretical occupancy, the achieved occupancy is going to be pretty low because one of the waves is not very full. In the case of the joint matrix multiplication, what brings down the occupancy is actually the number of registers that are associated with each thread. Each thread has 40 registers, right? Because we use a few extra registers to handle parts of the A matrix. And so it's not possible to fill up the GPU with the thread block size that we've specified. But one thing I want to point out to you is that this number of registers per thread is actually a lie. On our hardware, the kernel will actually use 2 additional registers per thread to store the program counter. So actually we're using 42 registers, 34 registers, and 34 registers per thread. The Nvidia architectural white papers will usually put this in as a footnote somewhere, so it's kind of difficult to track down, but just something to keep in mind. And so the final really nifty thing that the Nsight compute can do is tell you what instructions tend to take the longest amount of time. So in the top left, you'll see there's a little page button, and this is probably a little hard to see on this slide, but you can click on that and change that drop down to source. And then you'll be able to see some metrics associated with each line of the source code. You can compare the source code with 2 different kinds of assembly instruction. One is called PTX, which is sort of a higher level assembly code. It's a little easier to interpret. And one is the SASS, which is the actual binary code that the GPU executes. Typically I look at the PTX because it's good enough for my purposes. And this is really where that line info flag becomes useful, because now I can correlate the PTX code on the right of my window to the source code on the left of my window. And so to go along with that, I would like to point out that in your source code, there may be a certain line that causes many different operations in PTX, right? So this single line where we take a source value from memory, add some value to it, and store it again, this is going to be at least 2 loads. Well, it's going to be some number of operations to even compute what I is. Then it's going to be a load, an addition, and a store. Right? So there's many PTX instructions that come from this. And so that can mean that it will ascribe many different profiling metrics to this single line of code. And so what can sometimes help in some cases is if you separate, while you're profiling, just for the sake of understanding, you can separate out some of these operations so that they're on different lines of source code. And then each of these lines of source code will correlate to fewer lines of the PTX. So if you're having a little bit of trouble understanding where all the lines of where all the PTX instructions come from, sometimes it can help to separate out your line of source code a little bit. You may find that your Nsight compute does not automatically load the source file. That's because when you profile it on RAI. The path that the source file is on RAI is different than the path that it is on your own system. Luckily, you can hit this resolve button and navigate to the location of the source file on your own system, and then it will load up that source file instead. So this uses something called instruction sampling, which the way it works is basically every so often the position of the program counter is recorded in the program. And the insight is that an instruction that takes longer to complete will be more likely to have its position be recorded in this scheme. And so as the code executes, there will be many samples in the code, and the slowest parts of the code will have the most samples. So the way we can interpret these results is that the more sampling data that shows up in a particular line of source code or line of PTX code, sort of the longer that line of code or that instruction took to execute. And so if you click on one line of source code on one side, it will highlight all of the lines of PTX on the other side, and vice versa. But what you want to look at is the sampling data columns. And so this data column will tell you how many samples were there. And so the bigger the sample data column, sort of the longer that part of the code took. And then if you mouse over that column, it will show you the different reasons that the instruction was stalled at that particular line. So I can't really demo that on the slide, but if you take a second to look at this slide, you'll see that this column has many different colors in it, so these each correspond to different stall reasons. This is our basic matrix multiplication, and so this is the load and multiplication and accumulate that's in the inner loop. And so of course most of the time is spent there, because not only is the time for the 2 loads spent there, but that's also the multiplication and the addition. So it's not surprising that we can see that most of the time in the code is spent there. But this can give you a sense of what specific regions of your code are sort of spending the most time, the most active. And I don't show it in the slide, but there's very many different metrics that are recorded for each line. It will tell you the control divergence, the number of registers that are required at that point in the code, all kinds of things.